UFRAC team. I mean, it's the first PhD student actually in that session from the UFRAC project. He's at IMT Lucca, and he is talking today about a global local approach. No, it's not a global, it's the change of title, right? That's what you call it. So it's always good to look at this at the slides. So it's you're talking about phase field fracture modeling in large deformation solid shells with an efficient quasi-Newton solution. So I'm very excited to hear your talk, and yeah.
Thank you for the introduction. Okay. Hello everyone, my name is Zeng. I'm ESR 9 in the UFRAC training network. Currently, I'm doing PhD at the MT School for Advanced Studies Lucca in Italy with Professor Marco Paggi and the University of Seville with Professor Reinoso. The topic is phase field fracture modeling in large deformation solid shells with efficient quasi-Newton solution. So firstly, I will introduce about the research background. Single structures are widely adopted in the industry, ranging from aerospace engineering, civil engineering, energy systems, and automotive engineering. See the examples here. The Falcon rocket, the famous mushroom building structures in Seville, Spain, the photovoltaic module, the Airbus plane, and the race car. Most of the components are made of single structures. To better design these products, it's necessary to understand the fracture behavior of single structures, and a reliable simulation tool could be very useful. Regarding damage and fracture modeling, phase field approach has received a lot of attention in the past 2 decades. Here I will briefly introduce about the phase field theory. In the phase field approach, you can see the picture. The sharp crack in the potential cracked body can be regularized within a diffusive crack area. And the width of the diffusive crack area is the phase field length cube. So the energy function of the potential cracked body consists of strain energy functional, fracture energy functional, and external energy. And the fracture energy dissipated in the cracked surface can be approximated by the volume integral of the product of fracture toughness and crack energy density. And the crack energy density gamma is given by the last formula here, which is determined by the phase field variable and its spatial gradient. Here I will talk about the solid shell formulation. Compared with other shell formulations, the advantages of solid shell elements are twofold. Firstly, it can easily incorporate any 3-dimensional material law in a quite straightforward way. And secondly, only translational degrees of freedom is required, circumventing the difficulties regarding nodal rotations. So in the phase field, in the solid shell formulation, the position vector in the reference configuration, current configuration, and the phase field variable are determined by the interpolation of the upper and bottom surface vectors. Starting from the multi-field function of the potential cracked body, if we take derivative with respect to the independent field, we can get the first variation here with respect to displacement, phase field, and incompatible strain vector. To alleviate volumetric locking and point thickness locking, the enhanced assumed strain method is adopted in the shell formulation. So another independent field, which is the incompatible strain field, is introduced other than the displacement and the phase field. See the first equation here. Here I will talk about the finite element interpolation of the phase field solid shell formulation. So n is the shape function, and to alleviate transverse shear locking and trapezoid locking, the assumed natural strain method is also adopted in the shell formulation. See the green Lagrange strain vector here. To alleviate transverse shear locking, the strain components E13 and E23 are modified using the 4 collocation points A1, A2, B1, B2. See the figure here. And to alleviate the trapezoid locking, the strain component E33 is modified using the 4 collocation points C1, C2, C3, C4. Regarding the strain interpolation matrix, it can be obtained by taking derivative of the strain vector with respect to the nodal displacement vector, which is given by the last formula here. Due to the consideration of assumed natural strain method, you see the third row, the fifth row, the sixth row are modified accordingly. Besides the assumed natural strain method, as I mentioned before, to alleviate volumetric locking and point thickness locking, another enhanced assumed strain method is also adopted in the shell formulation. See the first 2 formulas here. M is the interpolation matrix of incompatible strain strain vector, which is transformed from the parametric space. And the interpolation matrix in the parametric space is given here. Here, 7 different enhancing modes are considered. J consists of covariant tangent vectors, which are defined as the derivative of a position vector in the reference configuration with respect to the parametric variable. And T0 is the transformation matrix. It consists of components of J matrix at the 0 position in the parametric space. Here I will talk about the weak form and the linearization of this phase field solution formulation. So first, the 3 equations here are the discrete form of residual equations with respect to displacement phase field and the incompatible strain field. Considering the irreversibility of a fractal process, a history variable is introduced to modify the phase field equation, and it can be seen here. To solve this set of nonlinear equations, the iterative neutral reaction solution scheme is adopted. The consistent linearization of the system is given here. K is the stiffness matrix, R is the residual vector. Since the inter-elemental continuity is not required, the incompatible strain equation can be condensed out in the element level. Here are the different components of the stiffness matrix. You see the C is the material stiffness matrix, and the matrix form is given here. And Q is the tensor product of linearized virtual strain and stress vector. The components of the Q matrix is the diagonal matrix, and the components of the diagonal matrix are given on the right bottom. See, due to the consideration of the assumed natural strain method, the 3rd row, the 5th row, and the 6th row are modified accordingly. Here I will talk about the Cauchy-Newton monolithic solution scheme. So in the phase field modeling, the two conventional schemes, which are staggered Newton scheme and monolithic Newton scheme, are widely adopted. However, there are both disadvantages for this solution scheme. For the staggered scheme, very small time increment is required, and it's usually it's very time consuming. And for the monolithic Newton scheme, sometimes it's very difficult to achieve convergence. So in this work, the Cauchy-Newton monolithic solution scheme is proposed for the solution of the phase field solution formulation. So see the first formula here. Z is the kinematic variable vector containing phase field displacement. R is the residual vector. And the approximated stiffness matrix is given here. In case of symmetry, the inverse of it, the approximated stiffness matrix can be found in the relevant literature. In this work, the condensed stiffness matrix is treated as the initial guess of the stiffness matrix. Here is the summary of the computational procedure. This is implemented into the commercial software ABAS as the user element subroutines. So firstly, we update the incompatible strain field, and for the different integration points, we compute the curvilinear basis in the reference configuration and the current configuration, and then we compute the strain interpolation matrix and the phase field gradient interpolation matrix. And then we modify the strain interpolation matrix according to the assumed natural strain method. And then we compute the material stiffness matrix, the stress vector, and the history variable. And then we compute the enhanced assumed strain interpolation matrix. And then we compute the elemental stiffness matrix and the residual force vectors with respect to displacement phase field and the incompatible strain field. Since the inter-elemental continuity is not required, the incompatible strain equation can be condensed out in the element level. And finally, we do the assembly. Here I will talk about the numerical examples. The first example is the very popular and challenging single edge notch here. See the schematic diagram here. The plate is discretized using solid shore element. And the right bottom part, the mesh at the right bottom part are refined, being 5 times smaller than phase field length field. The predicted contour plots of phase field variable are shown on the right. As you can see, the graph pattern agrees very well with the results in the literature. In the left bottom is the force versus displacement curves obtained from the Cauchy-Newton monolithic solution scheme and the staggered scheme with a different number of time increments. This green colored curve is obtained from the Cauchy-Newton monolithic solution. And all the other curves are obtained from the staggered schemes with a different number of time increments. As you can see, with the increase of number of time increments, the staggered solution gradually converges to the Colin-Newton monolithic solution. The total iterations versus the displacement curves obtained from the two different solution schemes are shown on the right. As you can see, the green colored curve is obtained from the Colin-Newton monolithic solution, and all the other curves are obtained from the staggered solution scheme. You can see the required number of total iterations for the Colin-Newton monolithic solution is almost equal to the staggered solution with 1,000 time increment. Computational times for the two different solution schemes are listed in the table below. As you can see, for the staggered scheme, it takes 1.5 hours, 2.83 hours, 14 hours with 1,000 time increments, 2,000 time increments, and 10,000 time increments. While for the Colin-Newton monolithic solution scheme, it takes only around 1 hour. So we can say the Colin-Newton monolithic solution scheme is much more efficient than the staggered scheme. Another example here is the cylinder structure under mixed loading. So you see the schematic diagram here. So there's a notch in the middle of the spaceman, and the vertical loading is applied to the notch. And at the same time, there's a tensile loading applied to the frontal end of this structure. This spaceman is discretized using solid shore element, and the mass at the potential craft area is refined, being 5 times smaller than phase field length field. And the predicted contour plots of phase field are shown on the right. In the left bottom is the force versus displacement curves obtained from the Colin-Newton monolithic solution scheme and the staggered scheme with different number of time increments. The green colored curve is obtained from the Colin-Newton monolithic solution, and all the other curves are obtained from the staggered scheme. As you can see, the same the staggered with the increase of number of time increments, the staggered solution also converges to the Colin-Newton monolithic solution. The total number of iterations versus the displacement curves obtained from the two different solution schemes are shown on the right. As you can see, the total number of iterations for the Colin-Newton monolithic solution is less than the staggered scheme with 1,000 time increments. Computational times for the two different solution schemes are listed in the table below. You see, for the staggered scheme, it takes 1.22 hours, 2.79 hours, 11 hours with 1,000 time increments, 2,000 time increments, and 10,000 time increments. While for the Colin-Newton monolithic solution scheme, it takes less than 1 hour. So the same conclusion can be drawn that the Colin-Newton monolithic solution scheme is much more efficient than the staggered scheme under these mixed loadings. So here are the conclusions of my work. So firstly, the phase field structure modeling with solid shore formulation is established, and then the two different solution schemes, staggered scheme and the Colin-Newton monolithic scheme are compared. And the performance of the two different solution schemes are investigated with different benchmark tests. It was found that the Colin-Newton monolithic solution is much more efficient than the staggered solution scheme. That's all. Thank you.
Yeah, thank you, Zeng, for that very nice presentation, which is open for discussion now. Other questions? Yeah, please.
If I understood you correctly, the runtime you showed, you only did one. You only listed one for the quasi-Newton scheme, but
yes,
a lot of difference for the others. I mean, with different time steps.
Yes. For the Colin-Newton monolithic solution scheme, even if you take 1,000 time, here it's only 100 time increment. But if you take 1,000 or 10,000 time increments, the results are the same. I didn't put the results here, but the results are same. But for staggered scheme, if you take different number of time increments, there will be some differences, and you must choose you must choose many time increments to achieve the converged solution.
Yeah.
So basically, the Colin-Newton monolithic solution scheme is much more efficient.
So its runtime is independent of the time steps.
For the Colin-Newton monolithic solution scheme, is true. It's independent of time size or total number of time increments. and it can overcome the convergence problems of the conventional
How can
Newton
it be
monolithic
independent of
solution.
the time steps? I mean, when you have more time steps, then you run, and it runs longer.
Yeah, it
And
runs
it has
longer,
to-
but the results are the same for the Newton monolithic solution.
Yeah, what do you mean with results?
You
mean
see,
the simulation outputs.
yeah,
I'm talking about the runtime.
runtime. For sure, if you take more time increments for the Newton monolithic solution scheme, the timing will be longer, but the results are still the same. You see the green
Yeah,
color
but
is over
basically
here.
you see how it scales the runtime. You have just presented one. I mean, it could be growing. Okay, I just say something with the power of 3. Then at some point, your method will basically the runtime will explode. Because I mean, I don't say that it is, but basically, this.
Okay, maybe we
This
can
didn't
discuss this.
convince me fully.
Okay, maybe we can discuss later.
Yeah, so maybe it's an option to continue the discussion in the coffee break. I mean, there was one question, maybe one short. But, yeah.
Yes, I was, maybe I haven't caught well, but are you using any energy density split for
Yes.
solution?
You see, for here, if without the energy split, it will not be the Zeng crack pattern.
Okay, and which
Exactly, right.
elastic energy density?
Volumetric split,
Okay.
the mirror split method.
Okay. So yeah, thank you, Zeng, for the presentation again.